we present our work, Model-Based Control with Sparse Neural Dynamics. Humans develop and maintain mental predictive models that help us understand the impact of our actions on the physical environment and carry out complex control tasks. An example of such tasks is playing pool. The observation of the environment consists of the positions of the balls on the table. Let's say we want to hit the red ball next. Using our brain as the predictive model, we predict the trajectory that the red ball is likely to take after being hit. Or, what if we hit the blue ball next? Our brain again would simulate the trajectory and help us decide whether this is a good strategy. How can we design and build similar mental predictive models for robots? Prior works explored using physics-based models to represent the dynamics of a system. While physics-based models have excellent generalization capabilities, they typically require full knowledge of the dynamics and access to the full environment state that is hard to obtain in many robotics tasks. Learning-based approaches overcome the limitations of physics-based models by learning a predictive model directly from raw sensory observations. Prior works examined using complex models, such as deep neural networks, as the function class. Despite their high prediction accuracy, deep neural networks are highly nonlinear, making model-based planning with neural dynamics models very challenging. Simpler models, like linear models, make solving for control signals more feasible and therefore are amenable to optimization tools with better guarantees. However, due to reduced modeling capacity, they often struggle to fit the observation data accurately. When employed within a feedback control loop, how accurate do we need predictive models to be in order to plan effectively and complete the task successfully? Our key insights are: robots should be able to predict the impact of their actions on the physical environment. Humans do not maintain highly accurate mental predictive models, yet we have unparalleled ability to complete complex long-horizon control tasks, since we take feedback from the environment for closed-loop planning, which compensates modeling error. And lastly, neural networks are overparameterized and can be sparsified with minimal impact on prediction accuracy. In this work, we examine whether we can take a step back on prediction accuracy in exchange for the use of more principled optimization tools and improve the closed-loop control performance. To learn a predictive dynamics model, we take a sequence of history, environment states, and actions as input to a predictive model represented as a ReLU neural network, which outputs the next state. The highly complex and nonlinear ReLU neural network makes it infeasible to solve for control actions using optimization tools with strong performance guarantees. Therefore, we propose to sparsify the predictive dynamics model in stages until the model is simple enough and thus feasible to solve with more powerful optimization tools at the cost of minimal degradations in prediction accuracy. In order to reduce the complexity of the model architecture, for each ReLU activation, we propose to either keep it as is or replace it with an identity mapping or a zero mapping. Compared to prior works, which required completely removing entire neurons to reduce computation, our approach is only concerned with reducing the nonlinearity of the model, while allowing substituting in identity mappings to maximally preserve the modeling capacity. We sparsify the learned dynamics model iteratively in multiple stages. In each stage, we specify a desired number of ReLU activations to remain in the model, while substituting the rest with identity or zero mappings. After the sparsification process, we take the sparsified dynamics model and reformulate each remaining ReLU activation as a set of mixed-integer linear constraints. We then use a mixed-integer program solver to solve for control actions that minimize the cost over the trajectory as part of a feedback control loop. We first evaluate our sparsification pipeline on two-dimensional piecewise affine functions. The task here is to recover the ground truth system from data through the sparsification process, starting from an overparameterized multilayer perceptron. A full model with 576 ReLUs successfully recovers the ground truth system. After sparsifying the model using our method down to 2 ReLUs, the highly sparsified model can still accurately fit the data. Next, we evaluate our framework on object sorting tasks, where the goal is to sort color-coded objects into corresponding target regions. We use a graph neural network to represent the dynamics model, and train using a dataset containing only interactions between two objects. The trained dynamics model combinatorially generalizes to predict the interaction up to 8 objects, and can successfully complete different variations of the task. We also test our framework on deformable objects. Here the robot is tasked with manipulating a rope to match various target shapes using a sparsified multi-layer perceptron to model the dynamics of the rope. Our framework also enables robot agents to accurately push objects to match various target poses. Leveraging environment feedback within a feedback control loop, the robot agent using our framework is able to adjust and fine-tune the pose of the object, even in the presence of minor prediction inaccuracies from the highly sparsified neural dynamics models. This also allows our framework to work with objects with more complex geometries. To summarize, we propose a method for sparsifying neural dynamics models to achieve more effective closed-loop model-based control through leveraging more powerful optimization tools with superior performance guarantees. Our method is generic and applicable to various neural network architectures, including but not limited to feed-forward neural networks and graph neural networks. Our method demonstrated competitive performance and combinatorial generalizability on a wide range of tasks involving rigid and deformable objects in scenarios ranging from single to multiple objects. Thank you.